the last session of ASPLOS 2024. This session will be on ML training optimizations. For the first paper, unfortunately, the authors couldn't be here. So Shixin Zhao from Chinese Academy of Sciences will be presenting on their behalf. Adios.
Hello, everyone. This is a talk of PrimePar in pursuit of better performing performance large language model training scales up in the training data size and model parameter size, making LLM training became extremely expensive. However, the certain LLM training system explores limited tensor partition space, including instances of expensive collective communication and tensor replication. This work addresses inferences by investigating better tensor partition solutions. Existing tensor partition distributes sub-operators along spatial dimensions. When two sub-operators generate potential sub-results, they require all reduce across divorces when they share same common tensor. The tensor is replicated across the divorces. In fact, these scenarios don't necessarily induce or reduce all tensor replication. Distributing these sub-operators along temporal dimension avoid both of these inefficiencies. This motivation leads us to explore spatial-temporal distribution of sub-operators. Here we introduce some notations. The spatial index D is a binary vector donating different divorces. The temporal index T donates the relationship mapping time of sub-operators partitioned from one operator. Thus, each sub-operator is indexed by dt, indexing the sub-operator running on divorce D at a time t. Each dimension of an operator has a dimension snide index, which is a function of D and T, indexing which side of the dimension that sub-operators dt holds. Existing spatial tensor partitions has been seen as a sequence of element-wise spatial partitions. Each elementary spatial partition selects a one-dimensional partition, and multiple such partitions are performed recursively. In this example, we first partition dimension n and then partition dimension k. After these two consecutive partitions, the arranged operator is partitioned to four sub-operators, each distributed to separate divorce for parallel execution. We observe the instance of infiniteness of spatial tensor partitions from the DSI. Firstly, examine the DSI of the summed over dimensions of matrix multiplication. Here, In can't take value 1 for divorce with D1 equal to 0 and vice versa. That means each divorce doesn't have a size to all sides of the dimension n, and all radius is required between the divorces with different D1. Secondly, examine the DSI types IN. It takes the same value for the divorces that has the same D1 but different D2, including the duplication of tensor with dimension Mn. In fact, influences donated by bullet point 1 and 2 are invisibly when you only consider spatial tensor partition. Inspired by Candle's matrix multiplication algorithm, we consider spatial temporal DSIs. You can see that In varies with temporal index T and takes all possible value at T variations. It ensures that for an divorce during its process of computation, it can has a size to all sides of dimension n to compute all the partial results and communicate locally. As small as the given time T, the DSI terms of any tensor is different for different divorces. Based on all these insights, we introduce a lower spatial temporal tensor partition parameter. With designing this parameter, we have three design properties. First of all, it has to be collective communication fair. We achieve this by letting DSIs of summed over dimensions variation with T to take all possible silence across time. Secondly, we avoid tensor replications by ensuring that for any tensor, this DSI tuple doesn't taking the same value under the same T and different RC. Thirdly, we ensure the tensor distribution between different training phases. Let's look in the details by examining the example of k equal to 2. We examine the combination function by checking which divorce back at the time t was holding the part of the tensor that divorce RC is at the time t plus 1. As for tensor I is DSI's match when evaluating RC plus 1t and RC t plus 1, which means that each It was has received I from this right label, notes that for the rightmost divorce, for example, divorce 0, 3, this right number is the divorce 0, 0. With similar recently, we determined that each divorce has received W from its bottom number. This communication allows cycle round patterns that are point-to-point and load data dependent on the computation result. Thus, we can be overlooked with computation by utilizing double buffer for tensor I and W. Forward step 2, 1, 2 are the same as step 0. Note that no communication is required in the last step of forward because only tensor W is used in both forward and backward, and we design DSI so that W distribution in the next step of forward matches that the first step of backward. In relation backward, DSI shows that the communication instructions are different from forward. Each divorce should receive W from these right top numbers, forming and circle communication rings, which different rings are labeled with different colors. One rings may not appear constantly. For example, the right top number of divorce 02 is divorce 33. These communications are also point-to-point and can be overlooked with computation. Backward step 1, 2 is also the same with step 0. The tensor W should reverse this intention distribution in the first step of forward. We adjust the W distribution in the last step of backward. Evaluating DSIs of the lexer and the first step of backward and forward for the W, showing that leftward shifter is required. Note we have designed DSI so that the tensor DO and I can be directly used when entering gradient space without any communications. Communication patterns theorem can be determined with a similar reasoning. The only special thing is that we end the delta term to the DSIs of IN and IK so that the DW distribution at the end of graduate phases is aligned with the intentional W distribution. The impact of this delta term on the communication is ending a leftward displacement to the communication directions in the second last step of the graduate. The delta term also results in the leftward shift of the final step's DW distribution compared to the parallel step. In the final step, computed while shifting parallels accumulated DW leftward. After that, ending the final step result with a shift DW. In this way, each divorce contains the final DW with its distribute alongside with the initial distribute of W. The key aspect of the course model is modeling the inter and inter-operator combination, and that is say inter-operator combination happening in groups where the grouping pattern is determined by the pattern strategies. We model the latency as a linear function of competition size. Since the grouping pattern determines the interconnection topology and bytewords within each group, we perform the separate linear co-inference for each grouping pattern. The number of grouping pattern is no greater than the number of divorces, making our profiling. Consider two operators N1 and N2 for each divorce. There may be same part of N2 inputs that is not locally available when finish the N1 computation, which requires communication. By evaluating DSIs of N1 output and N2 input, we can determine the length of intersection in each determined to compute the computation side. We model the inter-operator communication latency as a linear function of the total communication size. The total cost is the sum of all inter and inter-operator costs, so we aim to minimize the overall cost. However, the search space is that production of tensor potential space size of all operators is a complexity combinational optimization problem requires efficient optimization algorithm. In our theory, naive dynamic programming is too complicated. One operator's patient state should be kept in the optimal substructure until the iterator reaches the first target operator for its outgoing edges. To serve that, we utilize a segmented dynamic programming. This segment was selected such that within each segment, at most two operators, patient states need to be kept in the optimal substruct, namely the first operator and the operator as a current iteration step. Optimal substruct of optimization can be merged to compute large-scale subtractions. For transformer model structure, each transformer line only need to be partitioned into three segmenters. The operator substructure of a whole line is completed by two mergers. Since the transformer model consists of repeated lines, so we only need to compute optional substructure of the one line once and merge layers to complete the optimization of the whole models. We evaluate the training throughput and the picking power occupations of several transformer models compared to the best provide volume speed up and memory saving. And the improvements are also more significant when scaling larger models to more GPUs. From the latency breakdown, you can see that collectively communication latency is significantly reduced. Although extra point-to-point communication is introduced, this communication incurs small latencies and can be fully overlooked with computation latency. You can see that computation latency remains the same as the baseline. This indicates that the better utilization of communication resources PrimePar doesn't compares the efficiency of communication. Here we compare the kernel execution timeline of the MLP block when parallelizing to 8 GPUs, benefiting from the applications of spatial-temporal tensor partition primitive. PrimePar has significantly short communication kernels. Using PrimePar in a 3D parallel zone also speed up training. Note that larger models with 3D parallel offer PrimePar more optimization opportunities as they perform configurations with a higher degree of model parallelism. In conclusion, PrimePar explores the spatial-temporal tensor partition space and find novel partition parameters that are communication efficient and provide the possibility to better utilize hardware resources. We provide formulation of the spatial-temporal sub-operator distribution by which it is convenient to analyze the communication path. As a final remark, we have only designed our one parameters of the temporal spatial tensor partition space, and we think further exploration is worthwhile. And thank you. That's all. And I'm not the author, so if you have any question, please contact this email. Thank you.
Thank you, Shixin. Yeah, as the authors are not here, please contact the email for questions. Let's wait for a couple of minutes before we start the next talk. Zhenbo, you can get set up meanwhile. Zhenbo, where are you? Yeah, you can get set up. Let's wait a couple of minutes.
Hi, I'm Zhenbo from Tsinghua University. Hi, first screen investors. Okay.
I clicked the same button, it was not working. The next speaker is Zhenbo Sun from Tsinghua University. He'll be presenting their work on AdaPipe, optimizing pipeline parallelism with adaptive recomputation and partitioning.
Hi, I'm Zhao from Tsinghua University, and I am presenting a work with AdaPipe, optimizing pipeline parallelism with adaptive recomputation and partition. Recent years, the large language models have demonstrated powerful abilities with their increasing size and longer context. For example, the GPT-4 is estimated to have more than 1 trillion parameters and is pre-trained with the sequence length as more than 8,000. When training large models, it will consume a huge amount of memory, and the activations occupies a huge proportion. As we can see that the sequence length goes from the 4,000 to 16,000, the activations goes 4 times. Moreover, the pipeline parallelism will introduce imbalance memory consumption across different pipeline stages. So imbalance memory comes from the pipeline scheduling method. This is the 1F1B scheduling method, which is widely used to train large models. For stage 2, the workers, after computing the forward pass of the first micro batch, it can compute backward of the micro batch immediately, so it only needs to save the activations of one micro batch. However, for the stage 0, it needs to first compute the forward of 3 micro batches and wait until the gradient of the first micro batch passing from the last stage to the first stage, and therefore it needs to save the activations of 3 micro batches, and this results in the imbalanced memory consumption. Recomputation is a widely used technique to reduce the memory of activations by dropping the activations in the forward pass. For example, after computing the activations of the first layer, it will drop all the activations except the last tensor, and then it will use the last tensor to compute the activations of the second layer. And during the backward phase, during the backward pass, it will recompute the activations of the last layer, and then compute the gradients of the weights and the activations, and then process the previous layer repeatedly. And it is obvious that the recomputation will introduce more computation overhead. There have been works trying to trade off between the memory and the computation, but most of these works have the coarse-grained recomputation strategy, which means both the memory-intensive and the computation-intensive operators will be recomputed or not simultaneously. And other works will use the same recomputation strategy for all layers and all pipeline stages. There have been other works trying to balance the memory consumption across different pipeline stages. However, this work suffers from increased communication between different GPUs and inefficient pipeline scheduling methods. We propose AdaPipe, which use adaptive computation to partition the computation graph into fine-grained computation units and find the optimal partition to balance the computation of different pipeline stages. And let's start with the adaptive computation. It includes 3 steps. First is to partition the computation graph, and then construct the cost model, and then find the optimal recomputation strategy. We will partition the computation graph into fine-grained computation units. There have been some operators like transpose, reshape, that doesn't need to save the output tensors during the training, and we didn't show these operators in the figure. And other operators will become the boundaries between the computation units. And we can find that each output tensor only bonds to one computation unit, and if this output tensor is saved during the training, then the computation units will not be recomputed during the training. And then we can create the cost model. We use more to represent the set of the computation units within a computation graph. And we use R to represent the recomputed units. And then the complement set of R is the saved computation units. Then we can have the forward time and the backward time for each pipeline stage. The forward time is the sum of the forward time of all computation units within the computation graph. And the backward time is the sum of the backward time of all computation units plus the recomputed time, which is the forward time, which is the sum of the forward time of the recomputed units. Next is the memory model. So memory can be divided into three parts. The first is the parameters, gradients, and the optimizer states. This part is only related to the number of parameters within this pipeline stage and the parallel strategies. And the second part is the buffer to store for storing the recomputed activations during the backward phase. And the buffer can be reused for different when processing different layers. And we require AdaPipe to save the input tensor of different pipeline of different layers. And in this way, the memory buffer will be no larger than the sum of the memory consumption of the computation units within one single layer. And the last part is the activations, which is the sum of the memory consumption of the saved computation units. And this needs to be multiplied by P minus S, which denotes the number of microbytes that the pipeline stage S need to save. And then we can formulate this to find the best set of recomputation units with a set can minimize the recomputed time with the memory constraints. And this is actually a knapsack problem and can be solved by the dynamic programming algorithm. And we also model the adaptive partition by of the Y from B scheduling methods by split by split it into three phases, and we model the computation time of these three phases from the last stage to the first stage. And we can also formulate this as to find the best partition strategy that can minimize the running time of the first stage, as the first stage is always the slowest stage during the training. And then when finding the best partition strategy, we need to compute the forward time and the backward time of each pipeline stage, and this can be computed with the DP algorithm we mentioned in the adaptive recomputation. And finally, we propose a two-level dynamic programming algorithm that can find the globally optimized strategy, including the recomputation and the partition. And the searching time for the largest experiment in our evaluation only takes seconds. And the next part is the evaluation. We compare AdaPipe with Dathathri, which is just the one from the scheduling methods, and Chen, which is bidirectional pipeline scheduling method. And we compare AdaPipe with these baselines, both with the computation and without the recomputation. We also compare the AdaPipe with the A1 partition, which is the AdaPipe without the optimization of the adaptive partition. And we compare it, we evaluate these baselines with Llama 2 with 70 billion parameters and GPT-3 with 175 billion parameters. And the results demonstrate that AdaPipe outperforms these baselines by up to 1.23x speed up for the Llama 2 and even higher speed up with for the GPT-3. And we also evaluate AdaPipe cluster with more than 2,000 NPUs, and it shows that AdaPipe has a good scalability compared to the Dathathri. Actually, for each model and each sequence length, we will iterate all the 3D parallel strategies and choose the best one as the result. And it can be found that for the Dathathri with the recomputation, it can work for all pipeline it can work for all these parallel strategy. However, for the Dathathri without the recomputation, it is out of memory when the tensor parallel size is less than 8, because the smaller tensor parallel size means a larger activations. However, the AdaPipe and even partition can find better recomputation and partition strategies as when the tensor parallel size is 4. And we also analyze the memory consumption and the computation of different pipeline stages for AdaPipe and all baselines. And the result shows that AdaPipe and shows that each stage of AdaPipe can fully utilize the GPU memory to reduce the computation overhead. And the AdaPipe also achieves more balanced computation compared to AdaPipe without the optimization of adaptive partition. And for more details, you can find more details can be found in our paper. And thanks for your listening.
Thank you. Any questions? So I can ask a question. So, oh, there is.
Hi, great talk. I'm Christina from University of Toronto. So one question is, do you consider the memory swapping techniques like offloading the activations on the CPU side to resolve the memory capacity problem?
The activation to CPU. Yeah, it's a method to optimize this to solve the problem. But nowadays, with the high links and faster GPUs, so the PCIe bandwidth is a lot slower, and the offload is always cannot achieve better efficiency during the training. Yeah.
Okay. And I have one more. Yeah, I have one more question. Do you compare with manually tuned implementations of the LLMs like Megatron, ones that you can find from Megatron?
Developer on the Megatron, the Docker is also we use the Megatron. As the Megatron has implemented the 1F1B is the double, and we just compare with Megatron. Yeah.
Okay. Okay. Thanks.
Yeah, let me ask my question as well. So, do you have any ablation studies on memory versus compute trade-off set? Let's say I'm assuming you're utilizing the full memory. What if you say cut the memory by 20% or 50%? What would be the overhead in compute?
Sorry.
Let me repeat. So right now you're evaluating by utilizing the full GPU memory, right?
Yeah.
So what if you said the GPU had 80% of the memory that it currently has? How much would the training time increase by? Do you have any kind of ablation studies for that?
Yeah. It's actually if you have less memory spelled memory, and then the speed up will be smaller, and in that.
Yeah, I'm just asking how much overhead would there be in time if you cut memory by 20%?
Actually, it depends on the model. For example, if your model has a longer context and the flash attention will be the main cost of when you're training models, then our method can still achieve like more than 10% or more than 20% speed up.
Okay. Yeah. Okay. Thank you. Let's thank the speaker again. The next speaker is Zhaodong Chen. He graduated from University of California, Santa Barbara, and he's now at NVIDIA. He'll be presenting EVT, Accelerating Deep Learning Training with Epilogue Visitor Tree.
Is it possible to show the speaker script. Yeah, sorry about that. Yeah, I think they are under the.
I'm not actually sure because you shared it to me. These are the scripts, right? ASA. How about this CC?
I can present anybody else. Hi, thank you for coming. I'm Zhaodong. Thank you for my talk. And the title of my paper is Related Accelerating Deep Learning Training with Epilogue Wizard Tree. So in this paper, the background is that kernel fusion is very important. For example, if we fuse the multiplication with the succeeding kernels, and you can see we can skip the round trip of the intermediate result to the global memory. And this several things like it saves memory bandwidth and also reduce some host function overhead. But we found that despite the success in the inference, we found that we have some fresh challenges in the training scenario. So for example, the training graph is more complex and also have larger batch sizes. And because of these two reasons, we found that there are more challenges in generating fused kernels. So for example, in terms of performance, we found that fine-grained and domain-specific optimizations in CUDA are critical when the metamal and convolutions are involved. We also found that the flexibility is a new issue because there will be more fusion patterns under the more complex computation graph. And we need some more flexibility to cover different kind of patterns here. And besides, we also found that there are challenges to identify fusible subgraphs, such as so for example, in this fusion, it will create a cycle in the computation graph, and definitely want to avoid that. There's also something others, for example, sometimes we may have fusion plans that are conflict with each other. So for example, this greater than zero operator can either be fused with MM1 or MM5. And of course, our compiler should be able to identify which one is the best for the performance. With all these new challenges in the paper presented EVT, and EVT directly takes the joint forward and backward graph extracted by the torch compile. And then we have the graphical optimizations to simplify it, and we use the LP-based partitioner to partition it to fusible subgraphs. And then we also have the kernel level optimizations, in which we generate state-of-the-art fused kernels. And particularly we have the EVT operator compiler to address the challenges when creating fused kernels. And we also have the scalable LP-based partitioner to find the optimal partition of the whole graph. And besides, we have additional graph-level optimizations to uncover the hidden fusion opportunities. So let me give you more details about them. So let's start with the kernel fusion with the Epilogue wizard tree. The background is like traditionally, one common way to create these high-performance fused gem kernels will be using catalysts. And in catalysts, we have abstractions like we have the main loop template and Epilogue template. The main loop is basically the maximum multiplications or convolutions of these complex operators. We also have the Epilogues to represent the succeeding kernels to be fused to them. And this will definitely have the best performance because all these kernels are developed by good experts. But the major issue is the flexibility because each of these fusion patterns actually requires a new Epilogue template, which is non-trivial to develop. And our solution is the new abstraction, the main loop Epilogue wizard tree, and the new abstraction has already been added to catalyze in 3.2, and we support both Ampere and Hopper GPUs. So in this new abstraction, besides the main loop template, we instead offer a library of basic templates of like for basic Epilogue ops, for example, basic load store compute. And we also have template to allow you to connect them in arbitrary topology. In this way, instead of writing this new each template for the fusion patterns, we can directly connect this existing template. And this significantly improves the flexibility, but you still get the state-of-the-art performance from catalysts. So how these basic Epilogue ops are developed? So basically, EVT support any Epilogue fusion patterns as long as you can write it into a perfectly nested loop. And this actually covers a huge range of operators like optimized load store compute, forecast, and atomic reduction. And when you're developing these Epilogue operators by hand, basically you have to do a lot of loop transformations to match the main loop's parallelism and also perhaps tellings. And because we have the perfect next loop constraint, you can see after all these transformations, our statement still at the innermost loop structure, and we can definitely add more code to the other levels of loop to get better performance. So, for example, on the outer loops, we can create buffers and the chunks of data together to the registers, so that we can reduce the overhead to compute the predicates and also probably the pointer addresses. And motivated by this observation, for each epilogue ops, we have a CUDA template include all these definition of all these code blocks. And the only function that takes inputs and returns output is the visit, because you can see it represents the innermost loop. And in this strategy, we can divide epilogue ops for different kind of operations, and to use them, we can just get type alias. Yeah. And then let me talk about how to develop visitors that are template to connect all of your epilogue ops. But basically, they are just look like the epilogues I mentioned before. So they have the same set of number functions. But for all these functions that returns void, basically we just so you can see the visitor takes template arguments composed of the ops connect to it, and basically we just iteratively execute all these framework functions in these operators. The only exception is visit. Visit basically it represents the topology of these ops. Basically, in this paper, we have the tree visitors representing the memory function calls, and we also have the topological visitor to represent the arbitrary directed acyclic computation graph. Yeah. So let me give you an example to show how you can construct epilogue with the epilogue visitor tree. So I will start with this computation graph, and the first step is to rewrite it with all these visitor functions. So you can see after rewriting, basically it becomes a tree structure, and all these leaves are the basic epilogue ops. And then with this one, you can just define the type alias under the topological order. So it's this is all the code you need. So basically, it's very simple. You don't have to write CUDA to develop a new epilogue. And to make this automatic, we have a small compiler to do that, and we have 3 design goals. The first is to support different front ends. So, for example, you can direct convert your ASPLOS from PyTorch, or you can use your Python AST, drive from basic Python functions. And we also want to handle reshape and permute in this fusion process. Particularly, we want it to be automatic to enable the automatic selection of the right epilogue operator template. So basically, it should be able to distinguish between different kind of broadcast and reductions, especially when the reshape and permute exist. So to do that, we design a new which basically is a DAG, but and for each node we have 4 fields: name, shape, stride, and type, and the data type. And when constructing this, basically we just need the simple information like the stride and shape of the input and output node, and then we will automatically for the rest of them, and we will propagate the layout node to the away from the accumulator, and we have all of these layout transformation algorithms to recalculate the stride and shape of other nodes. And lastly, we can just rewrite the graph with the visitors and emit the CUDA code. Yeah, that's basically it. And then we also have the graph level optimizations. So the first optimization is loss elimination. What it do is it just return fake loss instead of the real loss returned by the loss function. So what's the benefit? So you can see with this example, if we decompose all these operators, because the loss is no longer needed, we can just do the dynamic elimination to remove the long and also the error loss. And this will bring significant speed up, especially if your loss function is the bottleneck. This could be, for example, the extreme classification models. The loss function can take up to like 60% of the execution time. But where we can return a fixed loss? This because the training will take millions of iterations, and actually the researchers will observe the average loss for every iterations. So why don't we just do a sample average, and this won't make much difference, right? Yeah, and the second optimization is the reduction elimination. So the idea is to form reductions that returns constant values. So in this case, you can see we have some that takes one hot tensor. The one hot tensor basically has one other entry per row. So the reduction will definitely return constant vector. So our compiler can automatically identify all these kind of opportunities. And it will definitely enable more fusion for UVT because as we mentioned before, UVT support atomic reductions, so the reduction cannot be fused with its consumers. And with this reduction elimination, you can see after removing the reduction of these operators after some max will be anti-wise, so we can do some simplification and fuse of them into fuse sometimes kernels. So you can see before we have 4 kernels in the advanced function and spectral path, and now we just have one fuse some max. Yeah. And this last part will be the external scalable LB-based partitioner. So the partition basically partitions the partition graph to subgraphs that can such that each subgraph can be fused into a single kernel. And we follow studies to have the LP-based formulation because firstly, you can see it ensures the optimal solution can be found because we can formulate our objective functions here. It also has the feasibility because we have the acyclic constraint. And we also have the extensibility, which is important for UVT because we can code all these rules to rule out the situations that UVT does not support. So can have constraint heuristics to say which node must be filled with another or it cannot be fused. So is this solved? It's not, because one major issue of this LP formulation is the scalability. So the LP formulation takes the cube number of decision variables of the number of nodes, so it's not solvable. Our solution is to divide the graph to weakly connect components based on the fusible edges and unfusible edges. So the first type is the edges where consumers cannot be fused with the producer. And second, we use necessary condition to rule out this kind of edges that will definitely lead to a cycle. And then we can just divide it into the weakly connected component, and we only solve the LP within each component will be no more than 10 or 20 nodes. And so before to do that, we will construct the possible passes outside of the component, and then we solve the LP and get the basic fusion plan. So to catch the solutions, we also use the with a lemon graph hashing to capture all these isomorphic components so that we don't have to solve the same LP for more times. And so for evaluation, we evaluate our compiler across 5 different models and we achieve up to 3 times on Ampere GPU. And so I want to end my presentation today with 4 takeaways. So UVT is a framework to fuse almost any combination in the Epilogue. Basically, you can have any-wise reduction broadcast, and they can be connected in a DAC formation. And we want to learn more about that. We have a GTC 2024 presentation from my colleague Jack and VJ to talk about how you can use this, along with a lot of new features in the Hopper GPU. You can also find more things on the Kata's repo. So although in this presentation, I only discussed about how to do this fusion on a single GPU. UVT can probably be used for the multi-GPU scenario. For example, you can use it for fine-grained overlapping between computation and communication because you can define these Epilogue operators that directly write completed tells to other GPUs with device APIs like MHMM before the whole gem is completed. So a proof of concept of this compiler is open sourced here. Thank you.
Thank you. Any questions? So in your evaluation, you just showed the absolute performance improvement. Do you have any breakdown as to which of these is giving, you've mentioned 3 different optimizations, right? Which of these is giving how much improvement?
Yeah, actually, we have the detailed engine study in the paper. So basically, for these 5 models, they have different features, right? For example, for the exponential is for the extreme classification, and the major bottleneck is the loss function. So the loss elimination brings a huge speed up. And for models like BERT, that's not the fusion like gives more credit. Yeah.
Okay, thank you. Any other questions? Okay, let's thank the speaker.
Thank you.
Okay, the last talk will be from Hongsheng Zhen and from Cornell University on SLAPO, a scheduled language for progressive optimization of large deep learning model training.
Hello, everyone. I'm John from. Oh,
I request everyone to go that side.
okay.
Yeah, you can get started.
Okay, thanks for everyone for attending our team last session. Yeah, so I'm Hong for Cornell University and I'm a third-year PhD student supervised by Professor Zhao. And today I'm going to talk about SLAPO, a scheduled language for progressive optimization of large deep learning model training. And this work is in collaboration with Toby, Shai, Chen, and Ida from AWS and Roshan. I think from the previous talk in this session, everyone in this room has already been convinced that the current deep learning models are too large to train, and it is not possible to achieve high performance without sophisticated optimization techniques. Currently, we have two kinds of optimization methods. The first one is manual optimization. Native PyTorch model often suffers from low performance, so programmers always integrate different optimization techniques to improve their training efficiency. For example, they need to manually merge several operators to conduct operator fusion, or partition the parameters onto multiple devices by hand to achieve tensor parallelism. This optimization is often require direct changes to the model definition, leading to thousands of lines of optimization code, which is not productive, highly specific, and hard to maintain, especially when the upstream model has been changed. Knowledge on Haoran can achieve high performance, but it requires users to rewrite their model to leverage the parallelism modules, which has low usability. The second method is leveraging compiler to optimize the model. When we use minimal engineering efforts from the model developers to achieve high performance, it is not always feasible to transform the model to a static computation path, and requires programmers to refactor the code. For example, not all the modules in PyTorch can be scripted by TorchScript, since it requires the forward function to satisfy certain constraints for control flow and pipeline notation. Moreover, the compiler optimization is often a black box. Programmers may find it hard to control their optimization granularity and reason about the optimization in the PrimePar optimized graph. Specifically, the alpha compiler, which is based on JAX, can automatically generate a parallelism scheme, but not many people in the industry leverage it to change models, as the programmers cannot see the effect of different optimizations. The details are hidden in the compiler process. To address the tension between training consistency and usability, we propose SLAPO, a scheduled language for progressive optimization, designed for large model training. SLAPO combines both benefits of manual optimization and compiler optimization by decoupling the model execution from definition. Slacker has a scheduler and autotuner and verifier to improve the performance and at the same time guarantee the correctness. Inside highlighted in PVM, Slacker decovers the model optimization from its definition and provides a set of scheduled primitives for users to easily conduct optimizations for large model training. With Slacker, users can load an existing PyTorch model as usual and create a schedule from the definition. But schedule and different optimization techniques that are used to improve the training efficiency, which are independent to the model definition itself. And that's why we can decouple it from the model definition. For example, here we load the first model for hacking first and create a schedule by passing the model definition. Notice Slacker preserves the hierarchical structure of the original module, so users can easily access the submodules using the same hierarchical structure. After they identify a specific in other modules, this includes single-device organizations like operator fusion and multi-device optimizations like different parallel schemes. These functions can be applied to arbitrary PyTorch models and thus greatly improve their usability. In the following, we use an example to show how to use Slacker to optimize a portable. We start from a single device optimization and let's look at the attention module. To achieve Haicheng efficiency, people may want to incorporate high-performance kernel from existing kernel libraries. For example, here we want to inject the fresh attention kernel to the bug model. We only need to access the submodule and then call the replace primitives to replace the whole module. Notice here we can directly schedule the modules and parameters, so there is no need to trace the modules, which avoids the limitations of the tracer. If users want to obtain the Dathathri graph to optimize their computation, Slacker proposes trace primitives to only trace the module by need, but will not import other submodules. We leverage project as the intermediate recommendation, and here shows the trace projection layer of the data module. After obtaining the static computation graph, we can do some graph level optimizations on it. Slacker provides a lightweight pattern language for users to easily specify the pattern and provide a fine primitives to retrieve the subgraph. For example, here we want to get the subgraph of dropout, layer norm, and residual add. We can directly specify the pattern and obtain the subgraph like this. Lastly, we can fuse the subgraph by calling the backend compiler. Mainly, Slacker supports PostScript and partially inverter in PyTorch 2.0, so users can directly do the fusion and print out the fusion graph like this. And we can see after this single device optimization, we can achieve 1.8 speed up compared to the vanilla model. Furthermore, we can optimize the feed-forward layer in the transformer model. It contains two linear layers, and we want to partition it onto two devices. We first partition the first linear layer to two devices by using the proposed shard primitives. Here, the first argument specifies the parameter to partition, and the second argument is the axis. We partition the weight and layers by column, since the weights are transposed in PyTorch, and the weights and the axis is 0. And then we go through the direct layer, which does not need further modification. For the second linear layer, we partition the weight along its row, so the axis is 1. Since the results are scattered on two devices, we still need to include an reduce operator after the second linear layer to ensure the results are correct. Slacker provides a sync primitive to achieve this by providing the mode and communication operation. Similarly, in the backward class, we also need to add an reduce operator before the first linear layer to ensure the correctness. After adding the tensor parallelism for the function module, we can already achieve 4 times speed up on a GPU server compared to the vanilla version. Similarly, we can also shard the embedding layer, and we can finally achieve about system speed up. And from this process, we can see that there is no need to trace the modules, and we only need 5 lines of code to replicate the tensor parallelism in Megatron LM. The shard and sync primitives can work for arbitrary models and parameters, and are able to express other complicated parallelism schemes like sequence parallelism. Furthermore, if we want to expand it to multiple machines, we can also incorporate pipeline parallelism. Slapper provides pipeline speed primitives to partition the model onto multiple devices in the pipeline. For example, here users can specify they want to split the model after the 11th encoder layer. Slapper can automatically split the modules based on the annotation and generate a computation graph on the right-hand side to make sure each device has the right modules. With Slapper provided primitives, we can apply optimizations for large model training in a systematic way. This dependent programming also includes auto training, auto scheduling for better performance. For the auto trainer, we can leverage domain-specific knowledge to define a intelligent search space, and Slapper leverage a randomized coordinate design algorithm to quickly find the optimal configuration. Further details can be found in our paper. For the experiment, we first conduct single machine experiments with up to a V1 GPUs. We schedule different language and vision models using Slapper with different parallelism schemes, including tensor parallelism and 0.3, and compare it with the state of the frameworks discrete and Megatron LM. While Megatron LM can only support 3 out of the 6 models, Slapper is able to support scheduling for all the models. And this speed can work for all the models, but cannot easily incorporate buffer-level optimizations. Overall, Slapper can always incorporate different parallelism modes to achieve the best performance and achieve up to 2.92 speed up compared to the baseline systems. We also conducted experiments on multiple machines. Again, Slapper can always apply the most suitable parallelism techniques to achieve the best performance, no matter if it is 0.3 or splitted parallelism. We show that Slapper can achieve 1.41 speed up on GB2 10B model compared to the Megatron LM with 64 GPUs, and it only requires users to write less than 30 lines of schedule code to achieve those complicated optimizations. To sum up, Slapper decouples model optimization from model definition, and it transforms a linear partition model to support efficient multi-device training in a few lines of code. Slapper also combines software efforts and outperformed disputes and Megatron LM. We also release our code. Please feel free to take a look. Thank you, and happy to take any questions.
Thank you. Questions? Any questions? So in one of your first plots, you showed Slappo and Slappo 03. Is your auto tuner choosing those, or are those manually determined schedules? So why do you have two Slappo TP and Slappo 03, right?
Oh, right. So in this experiment, we want to show that Slapper can simply integrate with different backend like Megatron and dispute. So no matter users choose different parallelism schemes. For example, they can choose tensor parallelism or 0.3 based on the model configurations and the hardware they use. And Slapper can always achieve better performance compared to the baseline systems.
Okay, makes sense. So what would the auto tuner choose in these cases?
For auto tuner, currently we only support tuning the the activation checkpointing ratio and also the batch sizes. And for the optimal parallelism schemes, this will be our future work.
Okay,
Yep.
thank you. Any other questions?
I have a question. Is that you mentioned that the usability of the alpha and the deep speed is not good. Is it? I wonder the usability here is for the users or the developers, because I think the alpha is very easy for users to use. You only need to add a Python decorator at the function.
Oh, right. So here for the usability, we mainly consider the efforts that performance engineers want to optimize the model. So for alpha, although performance engineers can directly pass in the model to the compiler, but they can only leverage the compiler to optimize the model, and they cannot just control the optimization by roadkit. For example, they cannot, for example, just optimize a local part of the model and check the performance of that local part. So, which means that if you if you use the compilers like alpha, then each time you can just apply the optimizations for all the models. Otherwise, you just lose all the optimizations.
Yeah, okay, I see. Thank you.
Any other questions? Okay, let's thank the speaker again.
Thank you.
And thank you everyone for being till the last session of ASPLOS. Thanks again.